So this lecture covered this concept of nuclear bombardment reactions, also known as transmutation. So this is basically how new elements are synthesized in a lab. So this was discovered in 1919 by Ernest Rutherford. So basically what he did is took a nitrogen-14 nucleus, which is perfectly stable, and bombarded it with helium, with alpha particle. So you keep in mind that means an alpha particle, not a helium atom, because it doesn't have any electrons. And what was discovered that this then was nitrogen is transformed into oxygen with the emission of a proton. So basically, how does this work experimentally? Basically, what's done is, I better not do that. So you basically have an alpha particle emitter, and I'm not sure what was done in this particular experiment. So some nucleus that emits, so it's radioactive, emits alpha particles. So you have an alpha particle that's ejected, and you basically beam that towards the nitrogen atom. So it's ejected from the nucleus of this radioactive element extremely fast. And nitrogen's a really small atom, doesn't have a lot of protons, only 7, so there's not a whole lot of repulsion that you have to worry about. So this alpha particle is coming out so fast that when it hits the nitrogen atom, it can fuse into the nucleus of the nitrogen atom. So then you have basically a nitrogen atom with 18 protons in it, or a mass number of 18 now. So and 9 protons in the nucleus. That's not stable, and so that then immediately decays into an oxygen 17 and atom, and a proton is emitted from the nucleus. So this is how basically the neutron was discovered. So beryllium-9 basically was put in the presence of alpha emitter, and the alpha particle bombards the beryllium-9 nucleus, and what comes out of that is carbon-12 nucleus, and a neutron is ejected from the nucleus of the atom. So of course the neutron, being a neutral particle, would not be deflected by a positive or negative pole of an electrode. So that would be experimentally how the neutron was discovered. So there's been over 1,000 different isotopes have been made by transmutation, by basically bombarding nuclei with each other. So there's a shorthand notation to represent transmutation. So if we take this nuclear bombardment reaction and write that in shorthand notation, then you write the nuclei that you start with, and then in parentheses you write the particle that's bombarded with, and then you write the particle that's ejected in the process, and then you write the nucleus that you end up with, would be the shorthand notation. So if we do that for this example, so we start with beryllium-9, we bombard it with an alpha particle, a neutron is ejected, and you make a carbon-12 atom. Okay, or if you're given the shorthand notation, then write the nuclear equation for that. So carbon-12 nucleus, so D means deuterium, so it's H2. So you bombard that with a deuterium particle, and then carbon-13 nucleus is made with the ejection of a proton. Okay, so how do you do transmutation experimentally? Well, you could do it just like we said, where you just have a nucleus and put it in the presence of another nucleus that's going to eject alpha particles, for example, and let the alpha particles slam into your nucleus under study. But if you want to do this for heavier elements that have a lot of protons, well, an alpha particle would come in and and basically just bounce off of that atom because of the so many protons in the nucleus already that there would be such a large amount of repulsion that the alpha particle would not be going fast enough that it could fuse into the nucleus of the atom. So in this case, if you want to fuse something like an alpha particle into the nucleus of an atom, you need to have it going a lot faster. And so to do this, you need something like a cyclotron. So Texas A&M College Station has a cyclotron institute where they can do these type of experiments at. So a lot of cyclotrons in the world, or you need a little bit bigger version. You would need what's known as a particle accelerator. So those would basically get these particles moving extremely fast, so they have a lot of kinetic energy, so that when you slam them into a heavy element, they have sufficient kinetic energy that they can fuse into the nucleus of that atom. So basically, it works some principle like this. You inject the particle, and then through a series of electric fields that you pass it through, you get it going really, really, really fast, and it gets into a bigger circular pattern. And then at the end, it comes out of that, and then you slam it into your sample, and they fuse, and then you monitor what comes out of the sample at that point. Okay, so how do you predict the product of a nuclear bombardment reaction? So if you had this example, so if you take plutonium-239, 94 protons, and get an alpha particle and a particle accelerator moving really, really fast. So basically you would inject the alpha particle here, and through the sequence of electric fields, get it moving really, really fast, and then you'd have your plutonium-239 set up here, and bombard the two, and then monitor what comes out. So what comes out of this is a neutron, and then a new element has been created. So what is that new element? How do you figure it out? Well, like we did in previous examples, if you take the sum of the superscripts, so 239 plus 4, 243, and then on the left-hand side you have a neutron coming out, so -1. So whatever this nucleus, whatever this new element is, has to have a mass number of 242. And then you do the same with the subscript. So 94 and 92 went in. So 96 on the left, and this is 0. So whatever this is, Z equals 96. So 242, 96. So then you look on the periodic table and see what element has atomic number 96, which is Cm. So that would be the new nucleus, that would be a new element that would be created in this bombardment reaction. Okay, so how do you detect radiation? So a couple of different types of instruments. One is called, one has what are known as ionization chambers, and one have what are known as scintillation chambers. So these radiation hits what's called a phosphor, and that's something that produces light. So we're not going to go into how those work, but basically just the radiation comes into the instrument, hits the phosphor, and that phosphor gives off light every time a particle, alpha particle or a beta particle or a neutron or something like that hits it. So let's go into how an ionization chamber works. So this would be a little schematic of an ionization chamber. So basically you have a tube with a small window that allows radiation to come into it. And in that tube, then you have a wire, which is an anode, and the tube itself, the surface, is the cathode. and then you have an inert gas in there like argon and BF3. So then your alpha particles or beta particles or neutrons come into the ionization chamber through that small window. So this could not necessarily be the best type of instrument for an alpha particle because they're really easy to stop, right? A few sheets of paper can stop an alpha particle, scan or clothing can stop an alpha particle. Depending on the thickness of that window, it may stop the alpha particle as well. But beta particles, neutrons, positrons can easily penetrate that window. But in some cases, an alpha particle may as well. So what happens once the alpha particle, for example, is inside the ionization chamber? Well, keep in mind that an alpha particle is really He2+. So if that comes into contact with argon, for example, what's going to happen? Well, which wants electrons more, helium or argon? Once you go up the periodic table, ionization energy goes down. So it's harder to ionize helium than it is to ionize argon. So what's going to happen is basically helium would take 2 electrons from argon. So you basically ionize argon. It may take 1 electron, it may take 2. So it may take 1 electron from 2 argons or 2 electrons from 1 argon, but the point is now your inert gas has been ionized, right? That's why it's called an ionization chamber. If you ionize something, that means it becomes positive, becomes negative. And so now in the ionization chamber, now you have your gas has been ionized. And so if you're, so now that can migrate to the cathode or anode surface. So that can then migrate to the cathode or anode surface, and now you've completed the circuit, so now you have an electrical signal, right? Or if a beta particle comes in, and hits your argon, then it could either add to it and make argon minus, or it could knock an electron off of argon. So again, you ionize the inert gas, and then that inert gas can migrate to, so in this case, migrate to the cathode and or anode and pick up an electron. So you've completed the circuit, and now you get an electrical signal. So how do you detect neutrons? So BF3 is added. So boron has a very high efficiency for fusing with neutrons. So if a neutron comes in to the ionization chamber and hits a boron atom, so BF3 would look like this, of course. So a neutron comes in, hits the boron 10 nucleus, and that would create a boron 11 nucleus, which is radioactive. And it would undergo nuclear decay to give a lithium 7 and an alpha particle. And then that alpha particle can basically ionize the argon or whatever the inert gas is. And so now you have an electrical signal if a neutron came in as well. Okay, so lastly, just a few comments on the biological effects of radiation. So of course, nuclear radiation is extremely dangerous. It can cause cancer. And of course, the biological effect depends on the type of radiation. Obviously, it depends on the dosage, how much a person would be exposed to, or whatever the organism is, the lethal time exposed to it. So one large dose is worse than a series of small doses, and that seems pretty obvious as well. So in terms of biological effect, it's measured in terms of what are known as REMs, so around 500 rems can be fatal, but damage can be detected with dosages of up to around 30 rems. So 30 rems and above is going to be pretty dangerous. So RBE is what's known as the relative biological effectiveness. So beta particles, gamma rays are the most safe of the radiations, although they're obviously not safe. But they have an RBE of around 1. Neutrons are more dangerous. They have RBEs of around 5. And alpha particles are the most dangerous. They have an RBE of around 10. But again, we made this point to begin with, that alpha particles are safe in the sense that they're easiest to stop because they don't penetrate skin or clothing. But if they're ingested and they get inside the body, where then they can come in contact with internal organs, then it's very dangerous because they're the most ionizing. So we're all exposed to some background radiation on a daily basis. So we're exposed to about 0.1 rem per year. So how are we exposed? We're exposed through potassium. So potassium is one of those essential ion elements that we must have in our diet. And it's quite a bit of potassium, around 0.015% natural abundance. For the potassium-40 isotope, which is radioactive. So we're all constantly, every single day, getting some potassium-40 in our diet. So we get a little bit of radiation exposure from that. Depending on where you live, geologically, if you live near uranium deposits, then there's going to be some radiation exposure from that. If radon gas, there's isotopes of radon that are radioactive. So if your home happens to be built near a geological deposit that produces radon gas, then that can be a problem. So some people, when you buy new houses, you have to have radon tested to see if your house has high quantities of radon gas in it. If it is, then you have to have a ventilation system in order to ventilate the radon gas out of the home, otherwise it can present a problem. And then we're all exposed to some radiation from nuclear fallout. So back when nuclear weapons were first being developed, they tested them in the atmosphere. And so that nuclear activity got up into the atmosphere then. So there's still some nuclear fallout from those nuclear weapons today. But that's gradually diminishing because atmospheric testing of nuclear weapons is now internationally banned. So all of the nuclear weapons testing goes on underground. So that'll minimize exposure since it's not getting up into the atmosphere as much. Okay.